Controlling the quantum world is now possible thanks to a material that responds to its environment, a phase-changing crystal that allows the manipulation of hybrid particles of light and matter. A new study demonstrates how a crystal that changes its structure depending on temperature allows the manipulation of hybrid quantum particles. This breakthrough could revolutionize the design of practical and affordable quantum devices. In science, some discoveries seem like they came from a laboratory spreadsheet, and others from an almost magical intuition. What if you were told that quantum particles, those elusive yet fundamental entities, can now be manipulated simply by taking advantage of a phenomenon we already know from everyday life, such as when water turns into ice or steam? That, in essence, is what a team of researchers from the Daegu Gyeongbuk Institute of Science and Technology, DGIST, in South Korea has achieved, using a material that changes its structure depending on temperature to control hybrid quantum particles, called polaritons. The work, published in the journal Advanced Science under the title Tunable Polariton-Rabi Oscillation in Phase-Changing Perovskite Microcavities, shows how a type of crystal known as perovskite can change its internal structure with temperature, thereby controlling the behavior of polaritons. According to the article, the Rabi separation energy of Exciton-polaritons can be tuned by up to 20%, and the corresponding excitonic oscillatory strength varies by 44% during the phase transition. This is not just a technical fact. It is a significant step toward the design of tunable, stable, and above all, more practical quantum devices. Polaritons, half-light, half-matter particles. To understand this breakthrough, it's first important to understand exactly what polaritons are. They are quasi-particles formed by the interaction between photons, light particles, and excitons, pairs of electrons and holes bound within a semiconductor material. This combination gives rise to particles that simultaneously have the properties of light, such as moving at high speed, and those of matter, such as interacting with other quantum systems. These types of particles hold great promise in fields such as quantum computing and ultra-fast sensors. In particular, they are relevant because of a phenomenon known as Rabi oscillation, which is a kind of back and forth between two quantum states. Being able to control this oscillation is key to any practical application. But until now, achieving this required very demanding conditions, such as low temperatures or complex devices. A material that changes with temperature. And with it, everything changes. The material chosen by the researchers is a hybrid lead halide perovskite, called MAPBBr3. The interesting thing about this compound is that its crystal structure changes with temperature, passing through different phases, orthorhombic, tetragonal, and cubic. In other words, the same crystal takes on different shapes depending on the environment, which affects its electrical and optical properties. This behavior is not just a curiosity. In one of these phases, the tetragonal phase, the crystal displays a property known as ferroelectricity. That is, it exhibits spontaneous electrical polarization. This characteristic, which does not require external electric fields, allows the interaction between light and matter within the crystal to be modified. As a result, the behavior of the polaritons traveling within it can be altered. In the article, the Rabi frequency can be probed by following the Exciton-polariton dispersion relation using Fourier plane spectroscopy, which allowed the authors to trace in detail how structural changes in the material affected its quantum properties. The microcavity, the miniature laboratory. To make all this happen, the team designed a device known as an optical microcavity, a structure where photons can be trapped and coupled with the material's excitons. These microcavities were constructed from several thin layers of reflective materials, called Bragg mirrors, separated by the perovskite active layer. This controlled environment made it possible to observe how the polaritons changed their behavior as the crystal transitioned from one phase to another. At low temperatures, the material was in the orthorhombic phase. Upon heating, it transitioned to tetragonal and then cubic. In each phase, the intensity of the Rabi oscillation, which measures how much light couples to matter, changed markedly. According to the study data, the Rabi separation energy decreased from 77 to 67 MeV in the orthorhombic phase, further decreased to 64 MeV in the tetragonal, and then increased again in the cubic. This variation reveals that the internal structure of the crystal directly influences the quantum behavior of the particles. Ferroelectricity, the hidden mechanism. The most striking finding of the study is that the appearance of ferroelectricity in the tetragonal phase is what allows the coupling strength between light and matter to be controlled. To verify this, the authors performed electrical polarization measurements and observed how it varied with temperature. The article states that the anti-correlated behavior between the excitonic oscillatory force and dielectric polarization suggests that the intrinsic excitonic property can be modified by the phase change of MAPBBR3. That is, when the crystal exhibits more spontaneous electrical polarization, the strength with which light and matter couple decreases, and vice versa. This is due to the way the charges are organized within the material. In certain phases, the electrical dipoles align, generating a net polarization that directly affects the excitons. In others, the charges are disorganized or symmetrically distributed, which changes the quantum landscape. Aplicaciones, computación cuántica y más allá. Este tipo de control, logrado sin usar equipos costosos ni condiciones extremas, es una promesa clara para el desarrollo de dispositivos cuánticos más accesibles y prácticos. En concreto, abre la puerta a fabricar chips cuánticos que funcionen a temperatura ambiente, algo que hoy sigue siendo uno de los mayores desafíos del sector. Además, la técnica podría aplicarse en sensores ultrasensibles, en sistemas de comunicación cuántica y hasta en inteligencia artificial fotónica, un campo emergente que busca usar luz para procesar información de forma más rápida y eficiente. En resumen, controlar las partículas cuánticas no tiene por qué depender siempre de campos magnéticos, láseres ultra rápidos o condiciones de laboratorio extremo. A veces, basta con un cristal que se transforma solo, como lo hace el agua al congelarse. Y eso, en el lenguaje de la física moderna, es todo un avance. Referencias: Hyun-Seo Choi, Minji Ko, Taejin Lee, Jinwoo Jung, Youngjun Lee, Hyunjung Jong, Youngjae Kim, Dongha Kim, Jinhee Hyo, Shinboom Lee, Jaedong Lee, y Changhee Cho. Exciton-polaritons oscillation in phase-changing perovskite microcavities. Advanced Science 2025. DOI 101002 ADVIS 20241 Sements.